According to Mary Meeker, internet analyst at Kleiner Perkins, Americans spend an average of 444 minutes every day looking at display screens. Meeker discovered this statistic in her 2014 Internet Trends study, and this number is most likely still rising. While it is alarming that Americans spend 7.4 hours each day looking at their tablets, smartphones, televisions, and computers, how many take the time to understand the inner workings of something so present in their daily activities? My goal is to explain the science behind liquid crystal state of matter and its function in the modern-day application of liquid crystal displays. I've spent an extensive amount of time preparing for this presentation by studying information from credible sources. The information I'll present to you I learned from the work of professors at Kent State University and the University of California, Davis. Today I will discuss three main points. I will begin by giving a brief history and the discovery of liquid crystals. Then I will discuss the science behind liquid crystals. Third, I will explain how liquid crystals are applied in the construction of liquid crystal displays. In conclusion, I will review the main topics of my speech. To begin, let's quickly review the history of liquid crystals. The initial discovery of the state of matter, now known as liquid crystal, was by an Austrian botanist named Friedrich Reinitzer in the year 1888. Reinitzer discovered the liquid crystal state of matter when he tried to measure the melting point of cholesterol benzoate that was extracted from a plant. Reinitzer came to the surprising conclusion that cholesterol he was melting had two melting points. When the cholesterol reached 145 degrees Celsius, it melted into a cloudy liquid. Once the cholesterol reached 178 degrees Celsius, the cloudiness of the melted cholesterol disappeared and it turned into a clear, transparent liquid. After Reinitzer made the initial discovery of this new state of matter, many scientists, physicists, and mineralogists have dedicated time and effort to furthering our understanding of liquid crystals. The scientists, physicists, and mineralogists that studied this new state of matter contributed to the classification of structural properties and have suggested the term liquid crystal. The most notable contributor to the study of liquid crystals is French physicist named Pierre-Gilles de Gennes. De Gennes has contributed to the development of liquid crystals since the 1960s. He was awarded the Nobel Prize in Physics for his work with liquid crystals. He developed a theoretical model for the properties of liquid crystals, which explain things such as their ability to scatter light. Now that we have briefly covered the history of liquid crystals, let's talk about the science behind them. Liquid crystals exist in a state between a solid and a liquid. Liquid crystals display qualities of a liquid such as high fluidity and coalescence of droplets. Coalescence is described in this picture. When you have two particles of a substance combined, they just become one daughter particle of the same substance. Just like pouring one glass of water into another, you get one big glass of water. In order to be a true liquid, it must be isotropic, which means properties are uniform, no matter what direction it's measured from. Liquid crystals display some physical attributes of a liquid, such as coalescence, but it fails to display attributes of the liquid on a molecular level. Liquid crystals display similar mechanical qualities to a crystal. They also display optical, electrical, and magnetic properties. The orientation or position of molecules in liquid crystals is controlled by weak magnetic fields. On a molecular level, liquid crystals display some of the properties of crystalline solids because they are anisotropic, which means their thermal and electrical conductivity varies with direction. This property gives liquid crystals optical properties. This property is also the basis for the technology in liquid crystal displays. There are many classes and subclasses of liquid crystals, but for the sake of time and the purpose of this speech, I will focus on the main phases of liquid crystals. When a liquid crystal is in a nematic phase, the molecules all have the same orientation. The orientation of the molecules is controlled by their polarity, and they are free to drift around. The alignment of these molecules can be controlled when an electric current is applied to them. That would be this third picture. The first two pictures refer to a solid state of matter and a liquid state of matter, so you can compare the molecules to a liquid crystal. A liquid crystal in a smectic phase has molecules arranged in layers. These layers can slip over each other, which is where the term smectic comes from, meaning soap-like, which is this fourth picture, you can see the different layers. The third phase, known as chiral or cholestric, causes a twist in the nematic phase structure. A liquid crystal in the chiral phase is best described as layers of molecules in a nematic phase. Each layer of molecules is turned at a fixed angle from each preceding layer. And as you can see, as the layers rise, they're turned at a fixed angle from each other, and that's going to be a cholestric phase. Let's take our understanding of liquid crystals and see how they are used to create a flat panel liquid crystal display. Liquid crystals do not have properties to emit light, so for a liquid crystal to display an image, it needs a light source. The materials that create a light source of the display is referred to as backlighting. The simplest liquid crystal display is a reflective display, which is right here. It means there is no internal light source. The backlighting is created with a mirror to reflect light from the user's environment. An example of a reflective liquid crystal display would be a simple calculator. The most common liquid crystal displays, such as LCD computer monitors, use fluorescent tubes as backlighting. These fluorescent tubes are placed above, beside, or behind the liquid crystal. That'd be this right here. Fluorescent bulbs are right here in the back. In front of the backlighting is the display matrix. So that would be all of these in front of the backlighting. So in front of the mirror, in front of the fluorescent lighting, this would be the display matrix. And it also includes the liquid crystal, as you can see here and here. Each liquid crystal display has a front and rear polarizer, and these control the passage of light. It determines if light passes as a color or as a black. Most common type of liquid crystal display is an active matrix or thin film transistor display. As mentioned previously, liquid crystals react to electrical conductivity to change the position of molecules in each of the phases. Liquid crystals react very predictably when an electric current is applied to them, which makes them great for this application. In a thin film transistor display, the conductive grid is used to deliver an electric current to the liquid crystals. There are thousands of transistors on this grid, and they hold a charge for a limited amount of time. There is one transistor for each color of each pixel. These transistors act very similarly to a capacitor. In this image you can see it says right here glass filters with polarizing films, so those would be the polarizers. And then here's the thin film transistor and electrodes, which sends the electric current to the liquid crystal. The grid of transistors controls the electric current to the liquid crystal, which controls the orientation of the molecules. The orientation on the molecules controls the intensity of light. The larger the display, the more transistors that there are on the display. According to Fujitsu, a Japanese information technology firm, they indicate that a display with a resolution of 1024 by 768, which is lower than a high-definition 1080p resolution, requires 2,359,296 transistors. In the front end of the conductive grid is the RGB mask, or the red, green, blue mask, which you can see right here. It is called an RGB mask because each pixel is broken down into 3 subpixels, red, green, and blue, which you can see here. The orientation of the molecules in the liquid crystal control the intensity of light to each subpixel in the display. So in each pixel there are 3 subpixels, and these subpixels are microscopic, and the intensity of light will actually control what color is displayed through each of these subpixels. And because there are millions of these subpixels, the human eye will paint this as a singular image. In conclusion, I will reiterate the main points of my speech. Liquid crystals were initially discovered by Friedrich Reinitzer in 1888. Liquid crystals exist in a state between a liquid and a solid. They have electric, magnetic, and optical properties. Their ability to scatter light through the manipulation of their magnetic fields is a basis for liquid crystal displays. Liquid crystals scatter light from a light source, either a fluorescent bulb or light from the environment that is reflected off a mirror. The thin film transistor sends electrical impulses to each transistor to manipulate the magnetic fields in the liquid crystals. This manipulation is what causes the light to be scattered in different directions and at different intensity. This light passes through an RGB mask, which gives off color. The human eye translates these millions of pixels into a singular image. I hope this presentation helped to give you a better understanding of how liquid crystal displays work and the science behind them. Thank you.